So what is problem solving? Well, problem solving is a cognitive process that involves the discovery, the description, the analysis, and the solving of problems. A good definition by Mayer is that problem solving is cognitive processing that is directed at transforming a given initial situation, a present situation, into a desired end situation or a desired goal situation. When there's no obvious method, no obvious way to arrive to this desired goal situation. Now, problem solving is often characterized as implying several different steps and different processes. For example, typically, a number of steps that are often described are that of problem identification. Really the question of, do we actually have a problem? Is this a problem that we need to resolve because there's no obvious solution? Then the definition of the problem and really the representation of the problem. So this is a representation of what exactly the problem is about. For example, what is the initial circumstance? What is the initial state, as we call it, of the problem? And indeed, whether we need to apply some kind of process in order to arrive to a desired goal situation. Then the next step typically is the construction of a strategy in order to resolve the problem. And this is really asking how a given problem can be solved. There might be several different strategies that might allow us to solve a problem, and we will discuss this a little bit later in this lecture. Then it's important to organize the information about a problem, and we will spend some time discussing this. And really, this is about understanding how the various pieces of the information of the problem fit together. What do they mean? In other words, what do we know? Trying to get a good understanding of what it is that the problem is telling you. So what do you know about the problem so that you can formulate, you can find a path towards a solution. Then, of course, the allocation of resources. This is really a question about, how much and what kind of resources you might want to allocate to a given problem. And then monitoring the problem solving, which really means asking yourself whether you're on track as you proceed and as you try to find your way through a problem towards a solution. And finally, of course, evaluation of your problem solving, which means understanding whether you have solved the problem correctly or if you have gotten closer to the solution. And of course, sort of I explained it kind of in this step-by-step way, but as this figure entails, very often problem solving does mean restarting or skipping from one point in this cycle to another. Now, when we talk about problem solving, most often we're talking about two different types of problems. The first type of problem is known as well-defined problem or well-structured problems. Now, these are problems in which the initial state, which is to say sort of where you're starting at, the set of operations or moves that are allowed for reaching a solution, in other words, the rules and the strategies of the problem, and the final goal state, which you want to attain, in other words, the solution, are clearly defined. So in well-defined problems, these three key aspects of the problem, the initial state, the rules and strategies, so the operations and moves you're allowed, and the solution are very clear. Now, a couple examples of these type of problems might be computing an algebra or a mathematical problem, playing chess is another such example. And these types of problems tend to be solvable through the use of some kind of algorithm. And you can just apply the algorithm and go from the initial situation to the solution. And indeed, computers tend to be very good at solving this kind of problem. You might remember when we spoke, when we began this class, we spoke about how certain problems like playing chess are effectively solved by computers, whereas other problems that are not as well defined as these kinds of problems tend to be easier for us to do, but much harder for computers. Now, one other example of these kind of problems is the so-called hobbits and orcs problem. And you might be familiar with this problem or know it by any other name. But it's a very good example of what a well-defined problem looks like. Because here, you know exactly what the initial state of the problem is. There are 3 orcs and 3 hobbits on the same side of a river and a boat. And you know exactly what the goal state, what the end state is. And you know exactly what are the rules to go from the beginning, from the initial state to the end state. And in other words, you know that you have this ship and you can only put 2 people at a time in the ship. And you also know that you cannot leave on either side of the river more orcs than hobbits, else the orcs will eat or kill the hobbits. Okay. So again, the initial state, the end state, and the rules to go from initial state to end state are very well defined. And this is the definition of well-defined or well-structured problems. And of course, you might be familiar with this, but you can find almost as an algorithm, you can really find your way through this problem in order to get to your desired goal state. Now, a different type of problem are so-called ill-defined problems. Now, these are problems in which at least one of those 3 key characteristics, so the initial state, the rules of the game, and the solution, are unclear. And see, these type of problems often do not have just one obvious correct answer. There might be multiple types of answers allowable. And there might also be many different types of solves that are allowable. And in fact, sometimes you're not even entirely sure whether you have reached the solution to the problem or not. And this tends to be much more typical of the sort of real world problems that you and I might encounter, you know, finding an apartment, relationships, deciding what school to attend, et cetera, et cetera, et cetera. Now these, as I was saying earlier, for us tend to be relatively easy to solve in the sense we seem to be well equipped to address these type of problems. But it's very hard for computers to address these kind of open-ended, often extremely vague types of problems. Here's one example of an ill-defined problem you might or might not be familiar with. Maybe if you've interviewed at Google, you're familiar with this problem. And it goes like this. 2 trains enter a tunnel 200 miles long, and they're traveling at 100 miles per hour. In fact, the 2 trains are traveling towards each other from the opposite ends of the tunnel. As the 2 trains enter the tunnel, a supersonic bumblebee flying at 1,000 miles per hour starts from the point of one train and heads very quickly towards the head of the other train. Now, as soon as it reaches the locomotive of the other train, it reverses course and very rapidly goes back towards the first train until it gets to the locomotive of that and sort of keeps going until finally the 2 trains meet each other and collide. Now, how far does the bumblebee travel until it meets its untimely end? And I'll wait a moment. Now, you might be tempted at this point to think about if the bumblebee is going at 1,000 miles per hour and it has to go sort of, might want to calculate how long it takes to go from the first train to the locomotive of the other train. And then sort of you might want to calculate this series, and as the trains approach and as the bumblebee kind of goes a little bit less in distance from one train to the next, how long does that take? And this might be the path that you might spontaneously have embarked on, trying to calculate this converging series of the bumblebee, doing segments that are ever shorter as the two locomotives approach each other. And of course, this is definitely not the right way of solving the problem. Or rather, it might be, if you're very good mathematically speaking, it might be easier to realize that the tunnel is 200 miles long. The trains are traveling at 100 miles per hour. So how long is it going to take for the two trains to reach the center, which means the point at which they will collide? Exactly 1 hour. So how far will our supersonic bumblebee travel in 1 hour? Exactly 1,000 miles. Right? Much easier. But it's clear that sort of the way in which you were to get to the solution of this problem was underspecified, was not very clear. The rules that you had to follow in order to get to the solution of this problem were definitely not clear. So this is a good example of an ill-defined problem.